Okay, next question, I believe it's the L2 question. We've got 0.6 liters of gas at 400 Kelvin, 133 kilopascals, and at constant temperature we want to expand this until the volume is, until the pressure is 100 kilopascals. Well, just immediately we can see that if everything else remains constant and only pressure and volume change, then the volume, well, the pressure is decreasing to 100 from 133. The ratio here is 4 to 3, this pressure being 3/4 of this pressure, very close to 3/4, which means that you're going to have 4/3 of the volume. You're going to expand to 0.8 liters. So we can immediately see that the pressure is going to go from, or the volume is going to go from 0.6 to 0.8 liters. Okay, the work is going to be the integral from V1 to V2, and that's going to be from 0.6 liters to 0.8 liters of nRT over V dV. Constant temperature, and it's a confined gas and remains constant. So we can do the integral. If we can evaluate nRT, okay, to get a numerical result, we got to figure out what nRT is. Well, how do we get nRT? Well, by the gas law, nRT is equal to PV. We're given the pressure and the volume at the initial state. So PV is 0.6 liters, the volume, times 133 kilopascals. The pressure, this is thousands of cubic meters. This is thousands of newtons per square meter, so that this product just comes out in joules, and 0.6 times 133 is very close to 80, so we get about 80 joules, and that's PV. It's not the amount of work done, that's just what PV is. Now we're going to integrate this expression. PV being 80 joules, nRT is 80 joules, so here we figure that the volume is 8 liters. We've already talked about that. Constant pressure, constant N means PV is constant, and from that we just have the ratio. PV being constant, P goes down to 3/4 of its previous, V goes up to 4/3, and 4/3 of 6 is 8. Okay, so nRT is 80 joules, so our integral of from V1 to V2 goes from 0.6 to 0.8 liters. nRT is 80 joules. And now we're just integrating from 0.6 to 0.8 liters, 80 joules over V with respect to V. 80 joules comes out. The integral of dV over V is just natural log of V, and we saw how the natural log works, so I didn't go through the details, but you should, to be sure you're used to them. And we get 80 joules times the natural log of 0.8 over 0.6, which I estimated to be 20 joules. Now I don't consider that to be a really accurate estimate. I'm pretty sure it's within 5 joules of being right, but that's our result. So it takes 20 joules of work are done in the expansion of this gas. Okay, expands from 0.6 to 0.8 liters against the pressure, and the pressure, of course, is decreasing. A little addendum: this is closer to 10 joules. My mental approximation went haywire, apparently. In any case, and I know what I did. Okay. So anyhow, that's the result. Now I'll also mention that this can be visualized as a curve on a PV diagram. Okay. nRT over V is going to be a 1 over V curve, a reciprocal curve, which you should be perfectly aware has this general shape. And we're integrating between V2, V1, and V2. In this case, that integral, the area under that curve, comes out to be 10 joules.